myself Dr. Preeti Trivani. I am from Department of Computer Science, Aryabhat College, University of Delhi. So in this series which is titled as Advanced Data Structures and Algorithm, today's topic is about shortest path algorithm. So in today's lecture we will look into the details about the shortest path algorithm, and then in our upcoming lectures we will be looking into the specific techniques of finding this shortest path. So let us begin our today's lecture and try to understand that what is this shortest path problem. So when we talk about shortest path problem in a graph, that is actually a problem of finding a path between two vertices, or we can say two nodes, such that the sum of weights of its constituent edges is minimized. So that means whatever there is the path from u to v, then the sum of weights of all the constituent edges which are in this, which are included in this path from u to v, that sum of sum of weights of the edges should be minimized. Now this is our the concept of shortest path problem. So shortest path problem, if we look into what kind of applications are based on the shortest path problem. So the shortest path problem in a graph is such a prominent and kind of well versed problem in real life applications. So for example, if we are building a road network, we can use the shortest path problem, or a network of logistics, a communication network, even a network of electronic design in which the pins are considered as vertices and there are wires or kind of the connections between them which are edges. Those kinds of networks also use this shortest path problem, and even any type of contingency analysis, community detection, or kind of power grid networks, all these are real life applications of shortest path problem. So when we define shortest path problem into in a mathematical term, so basically we say that the input to a shortest path problem is going to be a weighted and directed graph. Let us denote this weighted and directed graph by G, which is a set of V comma E, where V is, you all are aware that it is vertices and E are the edges, and every edge is also having a weight function. That weight function W is something that is mapping an edge from that weight function is mapping edges to real valued weights. So this is going to be an input to the shortest path problem. So we will be giving a graph of vertices and edges, and each edge is having a weight onto it, and that is actually a real valued weight. So this was about the input, what are we going to give to a shortest path problem. Then the weight which we are going to be determining. So weight for a path, for example, there is a path between the vertices V0 to Vk, and as I am talking about, it's a path, it could be, in some of the cases it could be one single edge, or it could be a combination of edges. So from V0 to V1, from V1 to V2, and then from Vk minus 1 to Vk. So we have a path P starting from V0 to Vk. Now weight of that path, which is denoted by W of P, will be the sum of the weights of its constituent edges. And if we are going to write it, or if we are going to represent this weight of the path mathematically, so we can say, so this weight of path is equals to summation of I is equals to 1 to k, summation of all weights of the kind of summation of all the weights of the edges between any vertex Vi minus 1 to Vi. So starting from V0 to Vk, whatever edges are coming into the path, we are going to sum those edges, and we are going to determine this weight WP. And finally, what are we looking for? We are actually looking for this minimum value of WP, because the problem is of shortest path. So, shortest path we are going to denote by delta U comma V. That means the shortest path weight from U to V can be is denoted by delta U comma V. And if we are going to define it mathematically, so this delta U comma V is the shortest path weight, and this is going to be infinity if there is no path from U to V. So, these U and V can be two disjoint components of or disjoint vertices of a vertex. If there is such a situation that there is no path from U to V, then the shortest path weight will be denoted by infinity. But if there is a path from U to V, then we will be looking for minimum of WP, where WP, as I have told you, is the sum of weights of the constituent edges of the path P. So, we will be denoting it by delta U comma V is equals to minimum of WP, where WP is a path between U to V. So, this path between U to V is represented by a wavy line from U to V, and that wavy line is having a written P on its top size. That means there is a path from U to V. So, if path exists, we are looking for the minimum sum of its edges. If there is no path from U to V, that means it is going to be infinity. So, this is what the concept of our shortest path weight is. So, shortest path basically we are defining as delta U comma V. Now, when we talk about these edge weights, these what are the edge weights, or what is why these weights are there, why these edges are being mapped into real value weights? Because these real value numbers, because these weights can represent so many things. So, weights can represent other metrics such as distances, they can represent distance between two vertices, or they can represent some time which is being taken from traveling from U to V. If I am talking about a transportation network, it could be a cost of kind of traveling from U to V, it could be a penalty, or it could be a loss, or any other quantity for that matter that accumulates linearly along a path. And the idea or the agenda is that we actually wants to minimize that particular quantity. Now, let me ask you one question. Till this point, have you have you gone through any kind of shortest path algorithm? That is the algorithm which is finding shortest path between the two vertices in a graph. So, if we ponder upon this question, we are going to get our answer that yes, the most simplest algorithm of graph traversal, which is the breadth first search or breadth first walk we can say, or breadth first traversal, is also a shortest path algorithm. The only thing is that works well on unweighted graph. That means the graphs in which each edge is having a unit weight. So, all the edges in a typical BFS scenario that we have seen in our kind of the series of data structures and algorithms. So, BFS is also a shortest path algorithm, but that works really well with unweighted graph. That is the graph in which the each edge is having its unit weight, because all the edges are unweighted, so we are assuming weight 1 for each and every edge. And in that scenario, your BFS is also shortest path algorithm, which starts from a particular vertex source and actually counts the number of hops in which you can reach onto a particular vertex. So, that is also a shortest path algorithm. Now, here when we talking about shortest path algorithms, we will find so many variants of this shortest path problem. So, the agenda for today's lecture, or maybe in the next one, we will be focusing on the single source shortest path problem. So, when I am saying single source shortest path problem, as the name indicates, let us say we have a graph which is given by v comma e, as it is denoted very commonly, a shortest path from a given vertex S which is belonging to the vertices set V to every vertex V, and that every vertex or all other vertices V are also belonging to the vertex set capital V. So, that is a single source a shortest path problem. That means there is one source and there can be multiple, or we are finding the shortest path from the source vertex, which is obviously going to be the given vertex, to every other vertex V in the vertices set. Now, when I am talking about single source problem, this may have different variants. So, the first variant is single destination shortest path problem. So, we have single source, and also this variant says single destination too. So, that means we are going to find a shortest path to a given vertex, let us say T, from each vertex V. And please notice that by reversing the direction of each edge in the graph, this can be reduced to a single source problem. So, when I am talking about single destination, that means there can be multiple sources and the destination path, destination vertex is one, and if I am going to reverse the direction of edges, this will be automatically reduced to the single source problem, because then we will be starting from one particular source and there are multiple we can say destinations. Then we have single pair shortest path problem. So, single pair, that means we will be looking for a particular pair, let us say u comma u and v. So, a shortest path from u to v for the two given vertices u and v, and all the known algorithms for this shortest path problem have the same worst case asymptotic running time as the best single source algorithms. But obviously, we will be looking into these asymptotic running times into detail after covering the algorithm properly, that is through a particular we can say dry run kind of thing. We will be looking into all these steps of the algorithm, and then obviously we will be analyzing the time complexity as well. Another variant of this shortest path problem is all pair shortest path problem. So, all pair shortest path problem that finds a shortest path from u to v, and here u and v will be kind of what will be the available values of u and v. That means we need to do it for every pair of vertices u and v, and this is actually, if you can see this problem in detail, this can be solved by running a single source algorithm once from each vertex. So, one idea, or the naive algorithm says, or the naive technique says, you can solve all pair shortest path problem by solving by running a single source algorithm once from each of the vertex. You can you can achieve all pair shortest path problem, but we have kind of faster techniques or faster algorithms to solve this all pair shortest path problem. So, if we talk about the variants of the single source shortest path problem, we have single destination shortest path problem, then we have single pair shortest path problem, we can have all pairs shortest path problem. So, this was actually, we can say kind of an introduction to what actually shortest path is, and how are we what all variants we can face, and we also looked upon the various applications of the shortest path problem. Now, when we try to kind of look into the problem of finding the shortest path into detail, we discovered one thing, that the shortest path problem possesses optimal substructure. Now, let me give you a quick recall that what actually this optimal substructure is. Optimal substructure is one of the key indicators or one of the key features of the problem that can be solved using dynamic programming and the greedy method. For both of the problem techniques, which is dynamic programming and greedy method, we need all those kinds of problems which have or which possess optimal substructure. So, the shortest path algorithms typically rely on the property. So, what is this optimal substructure property? Let us see, at least in terms of shortest path algorithm. The property that a shortest path between two vertices contains the other shortest path within it. Let me explain. So, for example, we have we need to find a shortest path from V0 to, let us say, V5. So, from V0 to V5 we will go to V1, V2, V3, V4, V5. So, while traveling from V0 to V5, the two vertices, let us say for example V2 to V3 will have the shortest path within it, then V3 to V4 will have their shortest path within this V0 to V5, or in simple words we can say that sub paths of the shortest path are also shortest path. So, that means if we have a bigger path and if we are looking into the sub path of this bigger shortest path, all other sub paths will be shortest path within themselves. Now, which kind of problem we are going to study for finding the shortest path problem or solving the shortest path problem. Now, the shortest path problem, as I have told you, that BFS is also a shortest path algorithm. Apart from that, in our previous series, we also looked into one of a very common shortest path problem, which was Dijkstra's algorithm. But the Dijkstra's algorithm puts up a condition on the graph that the edge weights should not be negative. That means this Dijkstra's algorithm works only when the edge weights are positive, we can say. But here the problem which we are going to deal with very shortly is the general case of the shortest path problem in which the edge weights can be negative. So, for example, now if someone asks that what kind of problems are there in which these edge weights are negative. So, for example, there is an edge from u to v and that edge is representing the profit which u has incurred in a transaction when that transaction is being done with v. So, for example, u has incurred a loss in case of rather than the profit, then the edge weight will be negative because that is indicating a loss. So, for example, minus x rupees is the x rupees u has lost. So, the edge weight will be minus x, and if that kind of in that particular transaction, if the vertex u has gained something or has earned a profit, then the edge weight is going to be x. If it is going to earn loss, then it will be minus x. So, having a negative edge weight is perfectly possible. So, some instances of single source shortest path problem may include the edges whose weights are negative. So, that means in these type of situations our Dijkstra's algorithm is going to fail here, because Dijkstra's algorithm does not work with negative edge weights. So, the graph or the technique the algorithm or the technique which comes into picture is Bellman-Ford algorithm that solves the single source shortest path problem even in the general case in which your edge weights may be negative. So, this is going to be our kind of agenda, or this is going to be our focus here, at least when I am talking about shortest path problems. Now, what kind of how these graphs kind of look like. So, here is a snapshot from the book Corman algorithm designed by Corman. So, here we have a graph. Here you can notice that between A and B there is a negative edge of weight -4. Then from D to C, again here is a edge which is having negative weight -3, and from F to E also and -6. Now, other side of the figure, which is having the vertices H, I and J, is basically showing that portion which is not reachable if we start from S. And please recall that a few minutes before we discussed that if the vertices, if the vertex V is not reachable from U, that means there is no path from U to V. So, for example, if I am considering my source vertex as S, there is no path to reach from S to H, or even S to I or J for that matter. That means H, I, J, they are not reachable from S, there is no path from S to H, I, J. That means here the kind of we can say delta U comma V, which is the path weight from U to V will be infinity, because these vertex are not even reachable. And here we have this again the edge from J to H is having a negative weight, which is -8. So, I have just given you snapshot of an of a graph which is having negative edge weights also, and there are some vertices which are non-reachable if we start from a particular source vertex, because this graph is having kind of we can say two disjoint components, one which is having S and another one, that triangle, which is having H, I and J. Now, coming to this Bellman-Ford algorithm, before going into this, now we need now we understood that these negative edge weights are perfectly fine. So, our Bellman-Ford algorithm is actually equipped to handle negative edge weights, but here is a disclaimer that the Bellman-Ford algorithm will not will not be able to find the minimum or we can say the shortest path if the graph contains a negative weight cycle reachable from that what single source vertex, which is U or S for that matter. So, if there is a negative weight cycle, so if the graph contains a negative weight cycle even reachable from S, then the shortest path weights we will say is kind of not well defined. So, what is the example of this negative weight cycle, that I will be telling you in a minute. So, if a graph, let us say G, consists no negative weight cycles reachable from S, then we can say for all V the shortest path weight remains well defined even if it has a negative value. That means negative value is fine, but if there is a negative cycle reachable from S, then we say the path is not well defined. So, here if you can see, we have vertices S, U, W and V. So, if we want to go from S to V, one path directly leads from S to V, that is a single edge, and the edge weight is 1. Now, if we take kind of we can say the longer path, that is from S to U, U to W and W to V, we will end up with a total sum of -1, which is 2 plus 3 minus 6. So, that is the shortest path not from S to V. So, these kinds of situation our Bellman-Ford algorithm is well equipped to handle. These kinds of situations will be handled by Bellman-Ford algorithm. Now here comes an explanation, because this is a negative edge weight, but not a negative negative weight cycle. What is a negative weight cycle? That I will be telling you in a minute. Now for example, we have a graph in which someone says that what if we kind of can we do something that let us operate each edge weight with a minimum number, so that every negative weight is converted to positive. So for example, here we have if we talk about the path between S to T. So the simplest path between S to T, here we have two paths. So from S to T, if we are going in the upward direction, we have the weight of 4 units. But if we take the path on the lower side, we will be having a kind of we can say the total path weight as 3. So the lower side path is kind of we can say preferable. Now in order to deal with this negative edge weights, let us suppose that we add 3 to the cost of each edge. So all the paths will become positive, non-negative, because minus 3 will be kind of 0, but it will change the identity of the shortest ST path. So the shortest ST path, then in that situation, if we are going to operate this figure, each edge in this figure by 3, then the shortest path will not remain as that of the in the previous situation when we have not operated. So we need a mechanism to handle these negative edge weights. That is one thing. Also we need to look into how these negative weight cycles, which are reachable from a single source S, are going to affect the kind of whole scenario of Bellman-Ford algorithm. That is still to be kind of looked upon, and because of the paucity of time, I would request that we will be joining in the next lecture to look into this negative weight cycles, and then after that we will be kind of digging more into our Bellman-Ford algorithm. Here is the list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. I will see you in the next. Till then, take care. Goodbye.